mention that this is one of a webinar series organized by in chunks of groups at AUST under the faculty or under the School of Engineering. Also, this group of research group, the DF Minerals and Materials Research Group, the AUST Barrage Research Group, also the Mechanical Engineering Department, are also doing this, with the Innovation Hub of the African University of Science and Technology, the AUST Inspire. And to that, and for that, today we have our president of the institution. I would like to just ask him to speak a few words, just to have him speak, and then shortly we would invite our guest speaker, who is also a proud alumnus of AUST. I think probably the first set of the alumnus of the AUST. So we are glad to have him speak to us today, and that I think that will be okay for now. So sir, Professor, President AUST, Professor Peter Onwalu, will you be able to just give us some few words before we continue, sir?
Yes, good afternoon, everybody. It gives me great pleasure to welcome everybody to this webinar. This is really very interesting, and as an institution, the African University of Science and Technology is at the forefront of generating and disseminating knowledge in different areas, especially knowledge in different sectors of economy of Africa. You may wish to know that the African University of Science and Technology is one of the African host institutions for PASSET, that is Partnership for Skills in Applied Sciences and Engineering. And that program, which is a World Bank supported program for the entire continent, has a number of universities in Africa as Africa host institutions. But they also have what you call international partner institutions who are collaborating with the Africa host institutions. And for us at AUST, our involvement in PASSET is in the area of materials and mining. So we are dealing with everything research, capacity building, innovation development in the area of materials and mining. This, of course, we know is one of the major challenges of Africa. I think I'm sure you hear about the resource cost syndrome. Africa is blessed with minerals, blessed with materials, all kinds of things, and yet we've not been able to add value, even extract these minerals, add value to them, and at the same time, we are importing all the products that come from these materials and minerals. So the area of mining and materials is really very key for the development of Africa. And doing this, building the body of knowledge that is required to deal with this issue is really very important. And there are various ways through which researchers try to make their contributions. Some are involved in the field work, trying to quantify, find where these materials and minerals are. Some are involved in experimental work, developing systems for value addition. Some are involved in all kinds of work. But today we want to listen to an approach which is using modeling and simulation to deal with research and problems in materials and minerals. The speaker I know very well. He's been one of our best minds in the area of in the area of modeling and simulation. And what I want to appeal to all of us who are in this call and those who will join, is that I'm seeing this webinar or presentation in two parts. One is the concept of modeling and simulation. And the resource person today is a very wonderful expert in this area. He has, apart from being a former student, is currently a visiting professor to the university. And I know he has done a lot in the area of teaching modeling and simulation for different applications. So we are going to be listening to what modeling and simulation can do, especially in these days of artificial intelligence. We need to understand how to build models, we need to understand how to do simulation for different purposes. And I believe that what we are going to learn today is very likely to also be applicable to other areas of research, not necessarily mining and minerals. And then, of course, the second part of it is we would have also been able to advance and disseminate knowledge in the area of mining and minerals, value addition, developing new materials, and so on. So I want to thank, good to see Dr. Nelson again. And I want to thank him for all the things he has done, even for our PhD students in the past. So we'll continue to collaborate with you. So once more, I welcome everybody to the webinar. I wish us a fruitful deliberation, gaining more knowledge in this field. Thank you very much.
Yeah, thank you so much. That's our president, and as you can see, our guest speaker is really welcome back. You know, he's really welcome home. You know, I don't even know what to say again about, or what to read again about his bio, about his profile. You know, our president actually, you know, said all of that. That is to tell you that, you know, he's really contributing to the success that we have recorded and are still applauding as AUST. He's not just an alumnus, he's one of the alumnus that have been contributing, and he's still contributing to the development of the university, and we really appreciate that. Because of in the interest of our time, I would like to have our guest speaker speak now. And then after his presentation today, I will ask few of our professors in the university to make some comments. That has been the framework for this guest, you know, for this webinar. The guest speakers speak, and I will ask our professors who are experts in the area of what has been said to make a few comments. Before then, I would like to quickly read you know, I will try to make it short, but you know, it's just like reading about, you know, a profile of an achiever. I will quickly read through that. So Dr. Nelson, he is an assistant professor assistant professor of of energy and mineral engineering, and the chair of the energy engineering program. Sorry, let me quickly mute. Yeah. It's a background noise. Okay. Sorry about that. So that is the chair of the energy engineering program in the John and Willie Leon Pamela Department of Energy and Mineral Engineering at Pennsylvania State University, the USA. He is also the co-director of ASEDA, that's the Alliance for Education, Science, Engineering, and Design with Africa. Before joining Penn State, he was an EPXRC Innovation Research Fellow at the School of Chemistry, Cardiff University, UK. Before that, he was a postdoctoral research scholar at the Department of Health Science, Earth, in Earth University in the Netherlands. Dr. Zade is recipient of several competitive academic awards and scholarship, including the U.S. Department of Energy. Sorry about that, because of background noise. So he is the recipient of several competitive academic awards and scholarship, including the U.S. Department of Energy Early Career Research Award in 2024, United Kingdom Research and Innovation Fellowship Award in 2018, the Dual Indian Professor Fellowship Award in 2020, and Overseas Research Scholarship from University College London in 2014. He received his doctoral degree in computational material science from the University College London, United Kingdom, Masters of Science degree in material science and engineering from the African University of Science and Technology, Abuja, Nigeria, postgraduate diploma degree in material science from the Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore in India, and Bachelor of Science degree in Applied Statistics from the University for Development Studies, Tamale in Ghana. Dr. Zade is the PI of the Materials and Minerals Theory Group, which specializes in the development and application of advanced theoretical methods and machine learning approaches to unravel structure property performance relationship in solid state material for application in solar cells, heterogeneous catalysts, high capacity batteries, and mineral beneficiation, often taking place in close collaboration with experiments to achieve a rational catalyst. The Zade's group has developed strong capabilities in first principle electronics, structural calculations, and microkinetic modeling to provide fundamental mechanistic insight into surface catalyzed reaction relevant to clean and sustainable processes to produce fuels and chemicals. His research work has been published extensively, over 120 publications in several high-impact journals, and communicated as invited talks at several high-profile international conferences. He serves on the editorial board of Modeling, Theory, and Computational Catalysis for the Frontiers in Catalysis Journal, and he is an associate editor for Engineered Science, Materials, and Manufacturing journals. Here today, I present before you our guest speaker, Dr. Nelson, and perhaps you do not know one of his other name is Dr. Nelson Zade. Please, the floor is yours.
Okay. Yeah, it's a pleasure to join all of you today. It's always exciting to be back home. I'll call it back home in this case, virtually back home, but it's always exciting to join colleagues. Will you allow me, please, to be able to share my screen?
All right. Go ahead, sir.
Okay, I'm just trying. Is it visible now?
Yes, so we want to have it in PowerPoint. Yeah.
Yeah, I'm going to project it.
Yeah, great.
Is it popping up now?
Sure, we got it. Yeah.
Okay. So yeah, let's get into it. Once again, it's a pleasure to join all of you as we talk about this important topic today. My slide is still at the middle. Good. So today, I'm glad that David could give an invitation that we could share some of the work we've been doing here in Penn State with regards to materials and mineral modeling. It's a very important topic dear to my heart. I inserted the word energy into the title, which was formerly not there, but most of the things we do here are mainly heavily energy focused. So the systems I'll talk about, the materials I'll talk about today are going to be energy materials or energy and mineral systems. So just to at least have some format or something that I'll be talking about today, I will be serving you a wide variety of meals today. So your stomach should be fully loaded and be more hungry to receive all the variety of food I will be serving you. So part of the menu today, as a starter, I'll be giving you some flavors to the energy transition, what we are going to be needing to be able to achieve the energy transition, what roles are materials and minerals going to play, and where we need to understand robust understanding of those systems. And then I will serve you a variety of main courses. One of them will be focusing on mineral surface chemistries and what kind of intricate chemistries happens in minerals and how do those things translate into their separation chemistries, or beneficiation chemistries, or flotation chemistries. Part of the heavy thing that within my group here is in solar cells. So we do a lot of design in new materials for solar cells, primarily focusing on surfaces, but more importantly on interfaces. So I will share some light about what we've been doing in that domain as well. And then I maybe give you some designs of catalyst design and some battery systems that we've been working on and why those energy storage systems are also going to be critical as we look at the energy transition. As said already, I lead a materials and mineral theory group here in Penn State, and heavily our job is mainly to use computer-aided design and engineering, where we want to use these approaches to understand material system, engineer material systems, optimize them for a variety of applications, some of which I'll share to you in the next slide. Currently, we do have a variety of talented students working in the group, and it's always my pleasure to appreciate them and to let them know that I do care so much about them and that they are part of the family and contributing to the success stories that we hear about. And talking about AUST for sure, Henry is one of AUST alumni, and I happen to get him here in Penn State. So he's been in the group and doing exceedingly well. So just want to give a shout out to him. The AUST alumni is growing significantly in Penn State as well. So we are forming our own community here and supporting one another and ensuring that we can all be very successful in the various fields that we choose for ourselves. So talking about my group, basically the Materials and Mineral Theory group, which we call the MMT group here, our principal areas of focus are typically in the thin film photovoltaics, which is in the first block. And there we are very interested in what is happening in the interfaces. How do two materials talk to each other? When you bring them together, do they want to remain married or do they want to divorce? And this kind of chemistries, we want to understand them. So we want to make sure that we are partnering the right materials with our principal absorber material in order to be able to design more efficient and stable solar devices. In terms of the second block, which is heavily what I gain a lot of expertise in from my PhD, heavily catalysis driven. So it's still very fundamental in the group where we want to understand heterogeneous catalyst design. A lot of the things we are interested in, how do we understand reaction mechanisms? How do we understand absorption chemistries? How do active sites and how we can tailor them to improve catalytic performances. In terms of the battery systems, we are also very interested in a lot of things that are happening in electrode-electrolyte interfaces. So there also we are very interested in unraveling interface phenomena, diffusion phenomena, absorption chemistries. And the last group I put there, even though it's the last, but it's not the least in the group, is something that is dear to our own heart, is what I call surface geochemistry and mineralogy. And a lot of my interests earlier days of my career began because I come from Ghana, and as you know, it from Continents, we do a lot of artisanal mining. So we do a lot of this in sometimes not being conscious about the environmental impact of these things. So we release all kinds of heavy toxic metals into our waste stream or water streams, which end up causing a lot of health problems. So one of the things I'm very interested in is developing absorbent material that will be able to pick up some of these heavy metals in wastewater from mining activities. But in general, the overall chemistry of mineralogy, how do we understand flotation chemistry, our reagents or ligands or collectors that are used in flotation chemistries? How do they react with our minerals of interest that we want to selectively pick? But the bottom line of all of these, as you see in the center, there is just structure, property, performance, relationships. And these are the things that we want to understand. So every material or mineral comes in a particular structure, and therefore that structure will dictate its property. Based on the property that it's inherent to it, that's the way it's going to perform. And it's the same thing we human beings are as well. Based on your DNA, your makeup, that's the way you're going to behave. That's the way we will see your performance in everything you do. So materials equally mimic us. And therefore, being able to unravel this intricate structure.
No, he doesn't want us to. He said AAF can make profits, but what he cannot do is for him to go and touch it.
Okay. Are we in another talk? I should continue.
Yes, please. Sorry about that. So I've muted everybody.
Okay. I hope the slides are showing, and as I move slide, people are seeing it.
Yes.
Okay, good. So those are the things that we want to unravel. And the reason why all of these things are very important is because of the key word I call here energy. Energy is behind, it's the power behind humanity. And it is what enables us to do everything as humans, and all the revolutions, industrial revolutions, and just to have a decent life, we need energy. But we will also understand very well that close to over 1 billion people are still without electricity, and this will happen in a lot of developing nations. And therefore, there's a need to be able to bridge some of this gap, and therefore understand what are the things we should be doing in order to provide this energy to a lot of people. Why do we care about energy? My interest in energy also stemmed from my humble beginnings, where I could grow in days where there was no electricity and had to study with kerosene lanterns and things like that. So you should see already why my appetite for energy and developing some of these cost-effective solar cells are also very dear to my heart. So the reason why we are very interested in all of these things is because we want to basically provide more energy to people. And energy is very important because it's the function, how much energy you consume is what is going to determine your well-being. And this plot is very important to me. I just want to show us to see that GDP per capita and power consumptions go along correlatively very well. So those countries that are spending a lot of energy tends to have very high GDPs. And because they tend to have high GDPs, so if you take, for instance, North America, where the United States, Canada, and all of those countries are, they tend to spend a lot of energy, but that's also translating into their GDP because they can do industrial revolution and therefore generates the national GDPs. But a lot of countries that are down the block, which are spending less energy, countries like Sub-Saharan Africa and South Asia, the Caribbean island, who are spending less energy, you will see also that the GDPs for those countries are very, very small. And because the GDPs are very small, it means investment in a lot of other aspects of our life and in our education, in our health, in all those things that will give us the human well-being are going to be diminished, are going to be minimized. And that's what you see in the right figure, where you look at Human Development Index and per capita power consumption. Again, that should translate very well. So you see the countries that are going to be spending a lot of energy are going to have higher Human Development Index. The Human Development Index simply has to look at aspects of your health, your education, your living standard. So if you're looking about health, even life expectancy at birth and all of these things, the number of years we spend in school, are all things that are a function of energy. So you see Iceland, Qatar, Norway, United Arab Emirates, the United States, which spend a lot of per capita energy, tends to have very high Human Development Index. If you plot them in a scale of 0 to 1, they are all close to 1. But then you come down to the block where some are even very close to 0.2, you see a lot of the countries tend to happen also to be from Africa. So, but that is also understandable because we don't produce a lot of energy. So energy is going to be key. But this energy, where are they going to be coming from? And those are the things that we want to figure out to understand. So the global energy challenge is something that it's inherent to all of us. It's not a problem for one person. It's a global challenge. Our goal these days is to provide clean energy, not just any form of energies. The energy has to be clean, it has to be sustainable, it has to be renewable. And these are the things that are posing a lot of scientific questions to us. How do we create these systems? How do we understand them in order to develop more resilient and robust systems that would do that? We've conventional dependent a lot of fossil fuel based, and this is continue going to be our major source of energy. But these days, because of all the climate issues that we see, there's a lot of antagonism rising up. But I would say that we need to be very cautious not to just bite off fossil fuel. They're going to still be part of our life. The challenge is because as we use them, we produce tons and tons of CO2 each year into the atmosphere. A lot of these CO2 molecules are very robust and stable, and therefore don't degrade out of the atmosphere. They sum up cumulatively, and that is leading to a lot of temperature increases, and also the negative effects that we see and hear about all across the world, extreme weather conditions. And this poses a lot of challenge why we want to make sure we do everything possible to keep our climate temperature rising not beyond 1.5 degrees C. And that's why the climate accord came in, that we want to do that. So, but we need to cut the emissions that we are releasing into the atmosphere significantly before 2030. If not, we might not be able to meet some of these targets that we set for ourselves. And because of all these challenges, the energy transition is becoming a very loud thing these days. Everybody's talking about it. We hear the word energy transition, and sometimes we think that it's just something that will happen today. It's something that we switch off one switch and switch on the other one. But that's not how it's going to happen. It's still going to be a slow process. It's still going to take a lot of things to achieve the energy transition. It has to be something we are innovating towards. So those are the things that's making that become very louder. The UN Secretary General made a statement sometime, which I think is powerful, but can also be misguided. It says that it's time to stop burning the planet and start investing in the abundant renewable energy all around us. The word that is misguided is stop. The key word is not necessarily to stop, because if we stop our fossil fuel infrastructures today, the whole world economy will come crashing down. Yes, we need to be investing in renewable energy, but we got to do that alongside the fossil fuel. So the goal will be our understanding to science as we amplify the renewable energy around us. This is because fossil fuel is still going to be part of our life. If you look at all the projections, you will see that even by 2040, still over 70% of the world energy is still going to come from fossil fuel. It's going to take us a lot to develop more renewable energy systems. And we still have a lot of fundamental science questions that we need to understand. And those are the challenges for us as scientists, but also opportunities for us to make lasting impacts. So I will always say this, that the key word is that we want to be innovating. We have to innovate, and it's not to stop, but we have to be innovating as we decrease our carbon footprint. So that is the reason why everybody's talking about the green economies, the green hydrogen, the green, all this green. We want everything green around us, the solar, the wind, the hydropower, the geothermal, the nuclear systems. But you will see very well that just being green is never going to be an easy thing. So Kemi the Frog has already warned us that it's never easy being green. And if it's not easy, it means that it's going to take a lot of radical effort, a lot of everybody's creativity, ingenuity, our ability to think outside the box as we design some of these green energy systems. So if we look at the whole sustainable energy future in a bigger perspective, we have a lot of things we need to be doing. We got to be creating solar energy systems. We got to be generating a lot of wind power. The nuclear needs to come into the picture. You will see that at the center of this thing is catalyst developments. We need to be able to take some of these naturally abundant resources like nitrogen, CO2 molecule, and water, and be able to turn them into useful chemicals and fuel. But these things are not going to happen in vacuum. They're highly energy-intensive processes, and therefore we need a catalyst to lower those activation energy barriers. So as we generate all this energy, we need to be thinking about how to store them. Energy storage is going to be critical. And that's why these days we have electric vehicles. But we have to develop battery systems that will be able to take care of all of those things. So in the heart of all of these things, you will see whether it's solar or battery or hydro, etc. The fundamental thing that cut across all of these things is materials and minerals. So materials and minerals sit at the heart of delivering the clean energy revolution. So you will realize that you want to produce energy, but you need materials to do that. And if you want to produce materials or minerals, you also need energy to do that. So it's like a chicken and egg problem. And that brings us to this energy materials nexus. And therefore, we're going to be battling with a lot of these as we design these systems. And we need to be mindful of the cost, the stability, and efficiency. These are the three tripartite relationships that we need to be working again. You can develop a very efficient material system, but it's too expensive, and therefore nobody will be able to use it in our day-to-day life. Sometimes you want to develop a material that is highly stable, but again, maybe the efficiency is very, very poor. So you're going to be, once you tune one parameter up, another parameter is tuning down. So finding these optimal regions where these things can work more efficiently is always going to be the challenge for us scientists to do. So talking about materials, again, for the energy transition, critical materials are going to play a lot of role. When we talk about criticality of material, it can mean a lot of things to different people, depending on the jurisdiction you come from. What may be critical to the United States may not be critical to South Africa, may not be critical to Nigeria. But the bottom line is when we talk about the energy transition, criticality is just a function of how relevant that material is to the energy transition. And the next thing will be what are the risks of its supply chain. Is it geopolitical? Is it just concentrated in one region where the whole world don't have access to? So those are the things that we talk about when we talk about criticality. And you can see that whether you are in solar cells or wind or battery system, you need a number of elements, critical materials. In solar system, you can see all these number of materials you need: aluminum, germanium, nickel, tellurium, silicon. All of them are needed. If you go to battery system, you're going to be needing a lot of lithium. You're going to need a lot of cobalt, a lot of nickel. And all these things are going to be challenged for us. The key will be, where do we get them from? Where do we find them? Are we going to recycle them? Are we going to continue to mine them? How are we going to do those mining activities? And those are all the challenges that we face. So if you take the battery systems, for instance, in our electric vehicles, I used to make this statement that the people who live in the industrialized world or in the West, they see only the clean side of electric vehicles. But all the dirty aspects of the electric vehicles are oblivious to them. It's completely out of their sight. Because a lot of these, the critical materials that are used in electric vehicles are concentrated in a lot of developing nations. And therefore, when those materials are mined there with all its devastation and consequences, they don't see that. They only see that, oh, it's an electric vehicle, it's clean, and they drive it. And the dichotomy is that many of the people in the developing countries cannot even afford the electric vehicles. So again, understanding the dynamics of all these in the supply chain issues that come along with it, it's something that we need to be having very honest conversations with ourselves as industry policies are enacted, as government policies are enacted, academia working to bridge all of these gaps, to making sure that mining or materials exploration is generally done in a more holistic and ethical way that is beneficial to everybody within the supply chain. So all these things bring to the question, are minerals the new oil? Again, it's definitely looking like it. You can see every country that has all these critical minerals are beginning to weaponize them. A lot of critical minerals are coming from China. And you can see sometimes when tension between the United States and China happened, all of them begin to leverage all these, their dominance over these. So they are becoming like the new oil, just like we've been using fossil from Saudi Arabia, Iran, Nigeria, which are going to be our economic backbones. We need to begin to see minerals equally as the new oil, because they're going to be the backbone of all the renewable energy technology. And if you do have a lot of them in your jurisdiction, the goal will be, how do you enact policies to be able to secure those things to the benefit of the nation and to the development of the countries. I talk about the human development index already. It will make no sense for us to have all these critical minerals in our jurisdictions and still remain having very low development indexes, because we are not able to add value to those materials. So there is going to be a supply chain issues, definitely, because the rate at which we want to develop renewable energy, we need a lot of things. There's going to be some deficits. The projection recently did show very well that by 2030, we're going to be in deficit of 46% of graphite, 42% of cobalt, 34% deficit of lithium. Nickel is going to be about 21% deficit. Copper is equally going to be important, but we're going to have a deficit. That simply means that the rate at which we want to utilize these critical materials or minerals is outspacing how much we are generating them. And that's the question we have to ask ourselves. Will the world have enough critical materials or minerals for the energy transition, as we are demanding lots and lot of it? Are we going to have enough of it? So that is the key question that comes to our mind. Are we going to continue just mining? What are we going to be doing? How do we understand this chemistry? And this is the way I put this statement by saying that today the data is showing a very looming mismatch. There's a looming mismatch between the well-strengthened climate ambitions. We have very big climate ambitions to address all these things. But the key question we have to ask ourselves is, do we have the availability of the critical materials that are essential to realizing these ambitions? But that also brings us a good news again, that if you do have them in your jurisdiction, it's time for you to begin to see that renewable energies are things that we're going to be talking about. And the essential components are going to be materials and minerals. So Gutierrez again made this very important statement that a well powered by renewable energy is a well hungry for critical minerals. So for developing countries, critical minerals are critical opportunity. We have to see them as opportunity, especially if we do have them in our jurisdictions, to create jobs, diversify economies, and dramatically boost revenue. But all this is not going to happen in vacuum if we don't have the right policies in place to be able to get them working in our favor. But and the next question, the next statement he made is, but only if they are managed properly. We got to manage these things properly. The race to the net zero cannot trample over the poor. Renewable energy revolution is happening, but we must guide it towards justice. And again, this statement, sometimes I will link it to what's happening in the DRC Congo, where we see a lot of forced labor, child labor, people working in hazardous conditions, producing over 50% of the world cobalt, yet remains to be one of the devastated nations across, in Africa. So these things are things that we need to be looking at in the bigger picture policies. But that just ends my kind of introduction to why we need to be caring about materials, why we need to be caring about critical minerals, and what we need to be doing to secure the supply chain to work in our favor. So to transition into science and what do we need to be doing to make these processes more efficient is to say that science has evolved. It's been always an evolving field, going through a lot of paradigms. And science has evolved over the years through 4 paradigms. In the early paradigms before the 1600, a lot of things were done empirically, where we do a lot of trial and error, serendipitous ways of doing things. But that paradigm is shifting. And then we move into the second paradigm of theoretical frameworks, where the physical laws of mechanics and thermodynamics and all of these things came into the picture. And therefore, we could tally those things to start to making some predictions. And then the third paradigm became heavily driven by computational science and simulations. And a lot of things happened in the angle of density functional theory, molecular dynamics, things that came into the third paradigm, where we begin to look at applying computation because of advancement in our computer processing powers. But we are currently in the fourth paradigm, which is data-driven intensive paradigm. It's a big data paradigm where artificial intelligence, statistical learning, data mining patterns, automation, and all of these things are also beginning to kick in. So you can see science is evolving. We can't just continue to stay in the prior to the 1600 era, because things are moving at a faster pace, and therefore we need to gain all this mastery of all these evolutions as we marry them together to understand systems properly. So for people who might be very curious, there is a very nice book written by Tony He called The Fourth Paradigm, Data Intensive Scientific Discovery. You might want to take a snapshot of that, and if you can lay hold on it, you will gain a lot of mastery, understanding, and the bigger picture to why the fourth paradigm it has arrived and is going to be leading a lot of charge. So coming back to the things we do, as I said, materials and minerals, whether you use these words interchangeably, they are the same to me. Whether we call them materials, whether you call them minerals, maybe they're coming from the natural sources, material because we synthetically make them, but they can be the same. So sometimes if I use materials, do not get worried that I'm forgetting about minerals. They just mean the same thing to me. So they're very complex in nature, and therefore we need a multidisciplinary approach as we try to understand them. And the key thing will be that it's going to definitely need a lot of marriage between the theory, which we are looking at the paradigms, marrying it back to the things that are happening prior before the 1600 experimentation. And this marriage is what is going to help us to understand materials properties very well. So we can use model system to understand how materials crystallize, how their functionalities dictate their properties, and therefore the way they behave. We can then take that understanding to go to synthetic labs and then begins to make these things, characterize them, and test them. And this knowledge sharing between experiment and theory is going to be critical as we move forward. I'm heavily focused on the theory part, where we want to use theory to understand material system. So if you come to the theory side as well, we need to be looking at things from a multi-scale approach. Not just one scale is going to give you all the understanding that you'll be needing. So in terms of material designing and multi-scale, we can look at things from the physics perspective where we're looking at electronic structure. Chemistry can also be, so these are the disciplines that are going to be playing a lot of role. Physics, chemistry, material science, and engineering are going to be disciplines that are applying these things at all across the scale. So we have the electronic scale, the atomistic scale. We can scale those things up to the micro scale and all the way to the macro scale. You will see that the behavior of something at the macro scale is just detected by what is happening at the electronic scale and atomic scale. So understanding what is happening between atom and atom, the language is speaking to each other. If we can decode those language, those secret language they're speaking at the atomic level, that's going to help us engineer the system to the micro and to the macro scale. So we have to figure out ways to do these things. And therefore, first of all, if you want to see how atoms speak to each other, one of the simplest ways to do that is just develop models that will describe how interacting elements work. And that's what was the early part of discovery we call molecular mechanics, which is basically application of classical mechanics to model chemical system. It's basically based on analytical functions, which is just a function of bond strengthening, bond bending, and rotations and stuff like that. So you will hear of things like the Lennard-Jones potential, which we could just look at to fix atoms once approach them together. There will be regions where they will repel each other. There will be regions where they will attract each other. Just this understanding can enable us to develop molecular mechanical approaches and simulate thousands and thousands of atoms with accurate precision. So that was the earlier part. And because of those level of understanding just by developing molecular mechanics, which is just based on just atom to atom interaction, it doesn't consider the electronics in those systems, but we can use them to really understand a lot of intricate chemistries. For instance, here, we could use them to perform molecular mechanics simulations of over 1 billion atoms, and those things are very possible with molecular mechanics. You look at things like protein folding, radiation damage, crystallization, and materials or minerals, correlated diffusions through materials, are things that we could use some of these systems to model. So those things have been applied a lot to solidification of ion in Finis, which is using molecular dynamics to really simulate these high-level sophisticated billion atom systems. But that will be possible with molecular mechanics. But when it gets to systems which are dependent on electron, molecular mechanics is not going to give you the answer. And therefore, you need to look at another type of models that will be interested to you, where you now want to understand how do electrons interact. Because how atoms interact is different from how electrons in those atoms behave, how they interact. And therefore, you will see that within the energy revolution, the area that I work a lot in, when you talk about solar cells, you talk about battery systems, you talk about catalysis, these things are heavily electron-driven processes. So therefore, you need to understand how electrons behave in this material system. So now you don't need molecular mechanics, but you need quantum mechanics. And therefore, when you need a quantum mechanical systems, that's where the complexity begins to come. You want to be able to solve these Schrodinger equations, which can be very complex and very difficult to solve. Very simplistic model where you take the kinetic energy and the potential energy with your Hamiltonian. You can then take that function and produce the energy within that system. When you know the energy of the system, you can then decompose and get all the properties that you are interested in. But to solve this very simple equation here, even for one electron system, can be a range of multiple partial differential equations, and therefore becomes sometimes very intractable to solve, even with your best supercomputers. So therefore, there's a need for a lot of approximations. And the best breakthrough that came in the 1964, developed by blessed memory of Walter Kohn, a Nobel Prize winner for chemistry in 1998, came up with the theory called density functional theory. So basically, when you take on a system that has a lot of many electrons in that system, we call the body perspective, interacting with an ion within the system, the question will be, do we want to explicitly treat all these electrons individually? That will cost us a lot of time to do that, because we have to be dealing with things that are in n-dimensional space. But then we can reduce that significantly to just 3-dimensional space if we treat all these electrons individually as the electron density. And just because he figured this out, that, even if we treat all of them as an density of electron interacting with the ion, which is why we call it density functional theory, that's the electron density, we can reduce the n-dimensional problem to just 3-dimensional problem. And that has become the revolution within the materials community that has applied to development of several material systems. So now what I would try to do is basically to let us see what are some of the applications of whether you're using molecular mechanics approaches or using quantum mechanical approaches to design systems or to understand materials or mineral systems. And the first one that I want to talk about or highlight quickly, I'm not going to give you through a few highlights, is mineral dissolution. So as we go to the mines and take up all these rocks and things that are of interest to us, we got to understand that the very element you're interested in is locked up in some rocks, and that you got to break all those rocks. You got to dissolve them even before you get the mineral of interest to you. So dissolution chemistry in mineral processing is always going to be very, very important. And a lot of these phenomena are going to be surface driven. And therefore, we understanding the processes that go into the mineral dissolution, how do we model those systems, are going to be critical. If you want to take a surface approach, you got to look at it that sometimes when a mineral is cracked or in one particular plane, you can have all kinds of things appearing in the surface. You can have add atoms, you can have terraces, you can have kinks, dislocations can form within the material, vacancies can be created in the material, add atoms can be created in the material. And all these dissolution chemistry, all these things are going to play a role as to what you're using to dissolve the system. Sometimes we use heavy acid and just dissolve the minerals completely. But those acids, the way they are doing that is basically attacking all of one of these, the kink, the dislocation, the vacancy, the add atom, in order to pull them out and break the material system down. So a detailed understanding of how surface structure is related to dissolution chemistry is very, very vital, and that understanding is needed. So in this area, there's a lot of work going on in this domain and space, especially when you want to load this. You want to do them at a very large scale, because these mineral processes, looking them at just a few number of atoms won't give you the bigger picture. So therefore, if you want to look at this in a proper way, we have to use things we call like molecular dynamic approaches to do them. But one of the challenges for molecular dynamic approaches is you have to develop how those atoms are talking to each other, which you call interatomic potentials. How do they relate? How kind of bond distances are going to exist them? So we have to be able to develop potentials that we have to construct to be able to perform molecular dynamic approaches. And one of the good things that is happening these days is because of machine learning. Machine learning has come to revolutionize the field, where we can now use machine learning approaches to train these potentials, to see how the calculator are going to be able to do this. So we can perform small calculations in a smaller scale, where we can perform ab initio molecular dynamics or do DFT calculations sometime for smaller system, and then use those data training to train machine learning force field that we can deploy for larger systems. So we can do training for a couple of ensembles, be able to train and see that the statistical deviations from what we expect them to be and what they're predicting are minimal. And these understandings help us to be able to select configurations that are able to train the models that we want. And as we do this, then we can now take those force fields that we develop iteratively from machine learning approaches, and now we can perform high-level molecular dynamic simulations in atoms exceeding 1,000 atoms for larger systems, and be able to see the trajectories. When I throw this mineral in contact with water, how is it going to react? How does the water help even in the dissolution? If I'm using an acid, how is the acid reacting? All are questions that just from understanding of DFT, molecular dynamics, machine learning, trained force field, we are able to do this very well. So typically, that's the workflow. So if you take any given mineral system like silicate minerals, which crystallize in this form, we have to understand what is happening at surfaces. How then do they interact with water if we want to look at the dissolution chemistries of these things? And this is a very important, especially for people who are in the cement industry as well. Silicates are typically the bedrock of the cement industry. So we want to see all of these understanding. And these are areas that computation is playing a lot of role, and machine learning is coming to help even speed up the accuracy and the time by which we develop some of these force fields as we perform large-scale simulations. But not only in terms of dissolution, we have to also be looking at it that these days we call some things rare earth minerals. Whether it's rare earth or critical material, one of the things that happen is that most of these processes are done through what we call flotation processes. And flotation simply, we want to be able to selectively pick the mineral of interest to us. So separating rare earth mineral from unwanted gauge are going to be things that will heavily rely on using selective binding collector molecules that are going to be absorbing to the surfaces of the materials of interest to us. So we understanding this integrated chemistry between our collector molecules and the minerals of interest to us is going to be critical. Because these days you can see that the mineral separation process is becoming very, very difficult, because maybe you want lithium, but that lithium is locked up with nickel, with cobalt, with iron, with chromium, and you want only the lithium. And the key will be what are you going to be able to use to selectively pick only the lithium? And that's why the questions are coming. So we have to be able to develop mild lascivium. We got to be looking at environmental sustainability, developing ligand chemistries that are more environmentally friendly, but that are also very selectively going to be able to pick the materials of interest to us. And that's why I call it a molecular level mechanistic insight is going to be very important as we rationally design future selective collector molecules for mineral or beneficiation. So if you take, for instance, bastanite is one of the key mineral that has the largest composition of cerium and lanthanum. We need all of these rare earth minerals, cerium and lanthanum, and a lot of other rare earth minerals are locked up in bastanite. But the key will be that if we want to selectively pick bastanite from all kinds of chemistry, we need to be developing collector chemistries that will be able to selectively pick that. So if we take a look at this work here, there's a recent work. We look at a couple of collector molecules and to see their selectivity towards these mineral processes. But that is a surface phenomena because they're going to absorb at surfaces. So your ability to characterize the surface of the mineral, your ability to understand the absorption chemistry of the various acids that you want to use to collectively pick this mineral, because you want a stronger reactivity between them. If your collector is not able to absorb to the mineral of interest, it's not going to help you to create that efficient flow flotation system to pull up the mineral of interest to the top for you. So here we can then use computational approaches, especially here in DFT approaches, to calculate what is the binding possible geometries of these acids, these collector acids, to the mineral surface. How strongly are they binding? Are they binding strongly, weakly, endothermically, or exothermically? These are all questions that we'll be able to unravel. And based on this understanding, we can see whether the proposed collector molecule is going to do the job that we want it to do or is going to fail drastically. So we can understand absorption chemistries and therefore create a proper understanding. And we have to look at it. The minerals, when you crack them or break them, they will cleave along different crystallographic planes. So it's also very important to know how does the same collector molecule absorb at different facets of the material. If you take for 101 or you're looking at 104 surfaces, they're going to have different absorption chemistry. It is very important to probe all of these things. And sometimes they're very difficult to probe experimentally. But with computation, we can do these things very efficiently. So once you understand these absorption chemistries, you can begin to go into the nitty-gritty to see what are the bond lengths, how are they binding? Why is a particular molecule going to bind stronger? Why is it going to bind weaker? What is detecting the absorption chemistry? Is it driven by electrostatics? Is it driven by electronics? Is there charge transfer dynamics happening? These are all questions that we would like to be able to answer as we design more efficient collector systems for our flow flotation processes. So just to wrap up quickly through this, just before I move on to some other aspects, computational chemistry is playing a lot of role even as we look at minerals and their behavior to biological enzymes. One of the minerals I work a lot in my career is iron sulfide. And iron sulfides have been very prevalent in nature. They have a lot of hypotheses around their life, playing a lot of critical roles in catalysis, in origin of life theories. But the key thing we want to see is if you want to say that iron sulfides will play a role in and maybe a CO2 reduction chemistries, the key questions are going to be how do we understand surface phenomena in minerals and how do they even compare to biological enzymes? So if you take a couple of minerals like makinawite, greigite, pyrite, they have a lot of structure similarity a lot to our biological enzymes, which are able to do all the things that we want to do. So biological enzymes are very good at taking CO2 and water and sunlight and turn them to glucose and all kinds of organic molecules. So sometimes we can take inspiration from these things and begin to mimic them. So generally, if we talk about CO2 activation, for those in the audience who don't understand that yet, I just want to say that it's a very simplistic process. But the key thing will be that you need a catalyst material that will be able to absorb your CO2 molecule, donate electron to it. That's what you call activation. You got to activate the molecule that is absorbing it on the catalyst surface. And then you can reduce it. You can either dissociate it or you can then hydrogenate it and convert it to a wide range of chemistries that are of interest to us. But to do that, we need to understand the material. So this material I modeled some time ago. The reason why I put it here is just to tell us something. It's a layered material system along the C direction. If you model this material using standard DFT, you see that the layer is kind of 5.6 compared to the experiment, which is 5.0. What it tells you is that if you ignore van der Waals interaction, which is holding the layers together, you're going to poorly describe that material. So therefore, when you're developing model system, you want to first of all understand the system, the chemistry of the system, the structure of the system, and therefore be able to impose the jacket or constraints that the model needs to accurately account for in order to be able to describe the system very well. But if you impose the van der Waals interaction, which this material need because it's a layer structure, then your C direction, the layers are held together in place, which is something that is very important when we model mineral systems. And therefore, you can cleave surfaces of this material, understand the surface topologies, we can understand the morphology of these crystals, and then see how does CO2 react with them. If you want to, say, use this for CO2 sequestration or for CO2 conversion, how are you going to do them? And therefore, we can begin to look at CO2 chemistry. If you take the 001 surface of this material, which is the dominant in the morphology, you see that it does not absorb CO2. But then you don't just stop there. We as modelers answer questions. We want to see, why did it refuse to bind? Why is it not binding to that particular surface? And then you can look at electronics and see that when you take the surface of this material, it's completely dominated or saturated by sulfur, which is heavily electron rich. And because they are highly electron rich, as you can see in the cartoon diagram there, if you bring CO2 close to it, the CO2 has a lot of electron densities on the oxygen. So negative will repel each other. So generally the CO2 is just pushed away because the surface says, I'm electron saturated, I don't need anybody. It pushes the CO2 away. So that's how we can begin to understand the chemistry and say, oh, so this is the reason why that surface isn't good. But if you take another surface of that mineral, yes, it's going to bind the CO2 molecule in different configurations. And the key thing I talk about is charge transfer. If you look at the second images there, that's how you see the microscopic view of how electron redistribution happens in the material when CO2 bind to the mineral surface. How much electron did the mineral give to it to cause it to absorb? And we can quantify all of those things, and that helps us to begin to tailor the material, tailor the surface chemistry, because we know a particular surface is not reactive, but another surface is reactive. So we can begin to say, how do we functional this material to make the particular surface that's more reactive become more dominant and decrease the surface that is less dominant or less reactive? All these chemistries are very important, and we got to understand them. So I will move off that quickly, but mention this about this particular system. I did model some time back when I was in the UK with ferrihydride. The goal here is to use ferrihydride, which is an iron oxide-based system for arsenic removal from water systems. So you can see that the intricate chemistry between iron oxide and aqueous media is going to be critical because they control the transport and the fate of all the contaminants in both our natural and anthropogenic systems. So we got to be, if you want to use ferrihydride, which is an iron oxide material to absorb arsenic from water system, then you want to first of all understand what is the surface chemistry of this material, how does water react with the surface. We can characterize these things in detail, understand the binding chemistry, how does water react with the surface, what kind of coordination chemistries are there, and then subsequently then begin to throw in arsenic, which typically crystallizes in the form H3ASO4, the most lethal form of arsenic that travels a lot in our aqueous system. We can then quantify the absorption complexations within this material and to see whether it's the ferrihydride going to be able to absorb the mineral or is the arsenic, or it's not going to absorb them. One of the things we learned from this work is definitely that ferrihydride or this iron oxide system are going to be playing a lot of role in arsenic removal from our water system, because a lot of them are able to bind this arsenic in the presence of water molecules competitively. So again, this is just a snapshot quickly to say that beyond understanding surface phenomena, we can also do all of these things that we do in experiment. We can simulate STM images that you can map up again compared to experiment, in providing you a lot of understanding that you need for some of these systems. This is just a quick, again, to see the importance of modeling. It's some work I did back sometime in 2016 where we modeled this material system we call marcasite and pyrite. And the storyline behind this is that typically pyrite is of interest for solar cell, but it hasn't been able to achieve those efficiency because in the early days, there was speculation that it's always come along with its sister. I call it a polymorph of it, marcasite. So marcasite is always coming along with pyrite, and therefore some people thought that if it's present in pyrite, it's going to deteriorate its performance, because the earlier experiment done on this material was in the 1980, and they predicted the band gap to be 0.34. Pyrite has a band gap of 1 electron volt. So the initial assumption was that if marcasite goes into pyrite, it's going to decrease the band gap and therefore deteriorate the photovoltaic performance. By 2016, I revisited that problem just to re-simulate this two mineral system. And what I found out was very intriguing, very exciting, is to see that no, that earlier prediction from experiments was actually wrong. That the band gap of marcasite is not actually 0.34. It should be 1.17. And we tested all kinds of our model to nail this down that this is true. It shouldn't be 0.34. And therefore, it means that if it's even bigger than the pyrite, therefore, if it's present in it, it should rather have a beneficial role, not a deteriorating role. And just around the same time that we did this work, we got it published in Advanced Material, there was a spectroscopy group that revisited this problem. And they were able to remeasure the band gap of this marcasite to say that, it should be about 1 electron volt or just over 1 electron volt. Just letting us to know that the things we measure, depending on the sophistication of tools we have, we may make wrong prediction, but that is when modeling comes in to revisit some of this problem and to bring those understanding. So we could model those systems. Now that we know that is true, I quickly reach out to my experimental collaborators and say, hey, guys, there's something exciting. Can you guys make this two system? Let's control the composition and test them for a variety of application. So we could model this system in terms of surface phenomena, their morphologies, and then simulate when the two come into contact. When you bring marcasite and pyrite together, how do they speak to each other? And it's, to our surprise, they want to marry. They form a very beautiful marriage at the interface, forming very perfect interface. And we can see that there's no corrugation defect or anything in the interface, which was highlighted by the red line. And because of that, we could do what we call band alignment, and to say that, when you couple these two material, the pyrite is even going to transfer a lot of electrons to your pyrite, and the holes are going to go to the marcasite. So you achieve what we call efficient separation of charges. And these things should translate to higher photo response. So my colleagues in the Netherlands were able to make those two mineral systems, mix them in different composition. And the bottom line, the summary is that just by doing that, we can increase the photocurrent significantly for the mixtures. And just because of revisiting that problem, because now we have robust understanding of modeling. So in the last few bits as highlights, I will just run them through in the interest of time, is that there are, this is why I'll call them materials. Again, they're still minerals. So some materials are emerging these days we call perovskite materials. But again, you can see that they lend credence to the natural system calcium titanate. So perovskite crystallized in this crystalline phase typically were initially discovered by Gustav, but named after his Russian friend Perovsky, and therefore the names became perovskites. And the reason why they become very attractive is because we want them for a wide range of applications in solar cells, in LEDs, in lasers, in photocatalysis. And all of these are very good. But intricately, these materials have come with two hurdles. They have a lot of instability issues, and they also have some toxicity issues because they come out with principal element lead, which is in them. So we need to be figuring out, even though they're as efficient as anything, perovskite solar cells are already reaching efficiency over 25, even outspacing crystalline silicon. So we have to be doing a lot of things to understand this material system before we can commercialize perovskite emerging solar technologies. And therefore, to do that, we need to be doing the following. We need to be understanding interface engineering. What is happening at the surface where all the things are going bad? Can we understand alignment? Can we understand interface charge carrier dynamics? How do we passivate the surfaces so that they can be more robust and stable? How do we mitigate ion direction? And all these barriers that come along with it. So interfaces are going to be key. And this is one of the areas that my research group is heavily focused in. So if you take a perovskite material, which is the absorber material in the bigger picture here, you generate electrons. But you got to collect those electrons, and you have to move the holes away in the opposite direction. If you don't correct them quickly, they're going to recombine. So if they recombine, it's just you've done a cost 90 job. It simply means you have not done anything. Your solar cell will give you an efficiency of 0. So your ability to collect these electrons as efficiently as possible or separate your charges is going to be critical. And that's why interfaces are going to play a lot of role in all the renewable energy technologies. So it means that we need to be understanding interfaces, what is happening at the interface. And this is a very difficult for experimentation because you have two materials locked hand in an interface region where most of our probes are not able to go to tell us what is happening in those domains. So we have been applying a lot of computation again in that domain to understand what is happening in these interfaces of this material. One of the systems we worked on recently was two material we call all inorganic perovskites, which have these polymorphs, the beta phase and the gamma phase. And typically, a lot of these two materials are the photoactive phases, but they can easily transform. They can easily transition into other phases which are not good for solar cell. So how do we mitigate them from transitioning to one another? So one way to do that is to create what we call heterojunction. Basically, marry the two together, create an electron-rich domain, and force them to stay in that phase so that they don't interface. So in a recent work we published in Nature Energy, we actually model those two systems where we can take the beta phase and the gamma phase and model the interfacial phenomena in the material. And what we learned from them is that, yes, these two materials would like to really marry together, because when they got married, they don't give to any babies with defects. You can see in the electronic structure, as I'm showing below there are no gap states in the electronic structure. Simply means there are no trap states that if you cite the electron, those states are going to trap your electrons. And the alignment is very good that we can transfer the electron from one phase to another. So with this, my colleagues in Chonam University in South Korea were able to make this material because of that understanding. They can grow these thin films by bringing these two materials together, forming heterojunctions of them. We call the beta and gamma based heterojunction based devices. And exciting news is that just by doing that, we can boost the efficiency of this thing beyond 21%. And even if you increase the device dimensions, efficiencies are still over 19%. And these devices are not just efficient, but they're equally very stable as well. You can run them over several hours and they still retain over 90% of the efficiency. So comparing those to other devices, you will see that our materials sit at the top of all material chemistry that are done in that domain. That work which we did recently, 2023, tend to have the current highest efficiency for that device just by combining modeling and experimentation. And that's what we published there. Just a snapshot, as mentioned, that Henry is in the group. Henry has been working a lot in the solar cell space as well. And just want to highlight a few of his work. He's been working on another system we call the chalcogenide perovskite, which are very important, very stable, very robust. But we need to understand them. They are emerging, therefore we need to understand what is their surface phenomena, what is their interface phenomena. And therefore Henry has done a lot of work throughout his PhD here, working on understanding this material system. One of his work has been published in Applied Energy Material, where he modeled the structural properties of this material, the band alignment properties of this material. But he took it further to now say, okay, if those materials are already very promising, they're very good, but if we deploy them in solar cell, they're going to be sitting outside where you have water and oxygen interacting with those material. Are they going to degrade? Are they going to destroy the electronic properties? So that's the next work he did, also unraveling the intricate chemistry between these environmental agents. And one thing we learned from them for sure is that these elements have some reactivity to the material, but they do not deteriorate the electronic properties of this material compared to the halide perovskite, which decomposes in the presence of these two environmental agents, which is a very promising work also he published recently in GFPhys Chem C. So in the interest of time, I will just highlight something briefly about catalysis. It's a very complex problem. We need to be tuning a lot of things to improve activity and active sites. So our work in this, my group also, we are focused more on CO2 conversion to fuel and hydrogen generation. Those are the things that we are doing. We want to tailor material property that will be able to do that for us. And hydrogen is very important to us because we do all these solar cells and all this green energy. We want to use them to split the water. So water electrolysis. Platinum is what we are using now. But is platinum going to be the answer? Maybe no, because platinum is the best state of the art for it, but platinum is highly expensive and it's scarce. So we got to find other materials. If you look at these volcano plot here, MOS2 kind of fall within close there. It's not as good as platinum, but could do some good job, as you can see there. So we've modeled a lot of those work as well. Some work we published in the ACS Energy Letter some time back was to take this material and understand the chemistry. Typically, when they make them, there's lithium present. But the question is the lithium a spectator or playing some role? So we model those systems. What role is the lithium playing? And the bottom line I want to highlight here in the interest of time is to say that when you populate this material with lithium, you donate electrons to the system. So you make the electron rich. And that is going to reflect on how hydrogen attaches to the catalyst. If your hydrogen binds too strongly, it's not going to be good for hydrogen evolution. So all the systems that have high lithium loading perform very poorly. And our experimental colleagues were able to make those materials and test them, and which correlate very well that when you're at low lithium loading, you can achieve high hydrogen evolution, which is reflected in the current densities. So we took it further to say, oh, what if the MOS2 is semiconductor, but what if we couple it with a metal and therefore develop what we call a Mott-Schottky junction, as we see here? We can be able to now even transfer electron more efficiently and therefore even drive the reaction faster. So that's what one of the PhD students in the group, Henry Nikhil, has been doing, modeling this intricate chemistry between MOS2 and support on cobalt sulfide, and understanding how hydrogen absorb and therefore how it will evolve over this catalyst surface. We can then marry this into our experimental work colleagues who also synthesize the materials that we predict and be able to show very well that yes, when you couple the MOS2 with your cobalt sulfide, the performance are generally much, much higher, even compared to some of the state-of-the-art catalysts like platinum. We are not too far from it. That if you have efficiency of the over potential of 55 for platinum, our catalyst is doing like 64%. So definitely that is already very good in itself just because of all those understanding. Your desert is to say that we need battery chemistries, but we need to be developing this very well as well. So one of the work we've been doing in that domain is what we call the lithium sulfur batteries, where one of the PhD students is working on. And again, the lithium sulfur battery simply means you're going to have a lot of parasulfide. We have a serious problem we call the shutter effect. And the shutter effect simply means that as you use your now sulfur as your cathode material instead of cobalt, but as you do that, the process becomes cheaper, but you're going to be generating what we call polysulfide. And this polysulfide will travel through the media and therefore can choke the battery and then bring the battery to its end of life. So we need to understand, develop other material, host material that will be able to absorb these polysulfide that are being formed. But then we need to understand how do they anchor, how do they absorb, and that's what one of these PhD students has been working on, understanding the chemistry between our material host of interest and the polysulfides that are absorbing these polysulfide. So overall, that has been an intriguing thing, just applying computation and experimentation in trying to understand how mineral systems and material systems work. So my key takeaway for us today is to say that there are a lot of exciting developments happening in materials and mineral modeling. And simulation is going to be playing a lot of critical role as we advance molecular dynamics, machine learning, artificial intelligence models, to be able to partner those things with experiment to give us a bigger picture of what is happening as we develop more robust mineral separation system, more efficient material system. And if we do that very well, then we can be talking about a greener mix where we need those materials or mineral to drive the energy transition. And I would just want to end by saying that computation is here to stay. We are now in that paradigm, the third paradigm of science. The fourth paradigm is here. We need to take advantage of it. And therefore, we need the human capacity development and knowledge development in those domains. It's going to offer us a lot of opportunity to span our parameter space so that we can lower both the development times as well as the cost. That's the key thing. We want things very fast. It means we need to lower the development times. At the same time, we need to lower costs. And computation is going to help a lot in that domain. I just want to end by acknowledging a lot of the work I highlighted were done with my experimental collaborators across the world. And just want to highlight them and the students who are involved in these projects. I want to thank our funding partners who have been very generous to us supporting the research we do, from EPRCC in the UK, the Department of Energy here in the US, and a variety of institutes in Penn State who have supported our work through seed grants. And I would just want to say thank you for your audience, and to say that my email is there, and I'll be happy to take some questions and follow-ups later through the email. Thank you.
Wow, thank you so much. And I also want to say that the guest speaker is also open to collaboration.
Yep.
Yeah, I'm currently with him at the Penn State. I'm visiting his lab and working with him on some of this work here. Yeah, that's what I mentioned. I think there are a few questions there. I will just quickly read that before we'll wrap it up for today. So a question coming up from Nkechi Ofiakalu. So she did say your lectures are always inspiring. Explanation comes very natural. That helps her to understand each of the phenomena, and she appreciates your previous support. So our question is regarding combining machine learning and DFT. What should be the first thing to keep in mind?
Yeah.
Or better to say, what should what to have as on hand before starting the project? What's to have before starting the project, especially for a beginner with less experience. So I think he's saying the basic knowledge she needs to have to do all those things. Yeah.
Yeah, that's a very good question, and thanks for your kind words. I would say that whether you are going to be thinking about machine learning applied to DFT or molecular dynamics, again, the fundamental to all of these is are just going to be physics, chemistry, and mathematics. That's the first. Those are the building blocks to doing all of these things. Many of you hear that my first degree was in applied statistics before I transitioned in material science. Somebody will say, "Why did he do that?" But you see that it gave me the very solid bedrock to all the things that I do today. So those will be some building block. So whatever discipline you are, I would say that you can be able to learn and learn some of the things that you've already acquired. But you have to see that all of these things are going to be data driven. And therefore, when we talk about machine learning models, they're going to be dependent on high volumes of data, not just any data, properly curated data that are very accurate in themselves and properly labeled. That is going to be needed. Sometimes we don't have those data. So therefore, you got to curate them. You got to generate them. You got to first of all start to build the models to do that. And that's why sometimes you start from a smaller scale model to be able to first of all understand in the small scale, how do these atoms talk to each other? What are the typical bond distances? So you can create data on just bond distances between different functional groups within maybe a molecule to a particular surface. So as you begin to curate this data, you can also then amplify it a little bit to maybe ab initio molecular dynamics, which is also still in a smaller scale. But then the key thing will be that you want to build these things from bottom up, not necessarily from up to bottom. And therefore, understanding what is happening at the smaller scale as you grow them gradually, trying to make sure that you understand what is happening at each level. Which data do you want to collect? Which data do you need to train a particular model? You got to be very clear about that. So for beginners, sometimes it's I will always say this is start with curiosity. It start with some motivation, like I want to learn this. I will use myself as an example to you. When I moved into material science, I had zero knowledge about material science. I remember when I was at AUST and I told the president, Carl Voltaire, that I want to change from mathematics to material science. He was like, Nelson, you are crazy. You are very good in mathematics. Why do you want to go to material science? But it took a lot of determination. I said, no, that's what I want to do. So that determination led me to dive deeper into this knowledge because I made a decision I want to do it and therefore have to pay the price for it. And therefore, sometimes aligning yourself with like-minded people, learning under some people. These days, all the things we want to learn, there are very good information out there for us. Sometimes you even have somebody to hold your hand. And that's the reason why sometimes maybe I'm there, sometimes maybe why some students from AUST are in my group. That may also hold your hand. So that's the reason why we are there to help one another, especially those who are at the beginning stage, materials to start with, resources to start with. And if we do that, I think once your curiosity becomes so high, your appetite for the knowledge becomes so high, you can get it. You'll get it done. Yeah.
Thank you so much for that response. Also here, we have a question from Safanaya Jibade. His questions, or better to say, a question is a nice presentation from the participant, and he's saying, my question is, how does mineralogical composition of the material systems influence the selection of collectors, and what role does atomistic simulation play in aiding this selection?
Yeah, now that's a very, very, very good question. Again, so just as I told you already, every material or mineral comes with its own composition. We all have our DNA. So minerals also have their own DNA. It means they're going to be made up of their specific compositions. And sometimes, either based on experience, we know that if a material has so-and-so elements, it may have so-and-so affinity for this particular type of molecules that will come with certain functional groups. It's all about functional groups, it's all about functionalization. So sometimes because we don't understand which functional groups are going to be more selective towards a particular mineral of interest, that's when computation comes in. Because computation, you can have the same molecule, but maybe it has a thiol functional group, it has an amine functional group, it has a carboxylic functional groups. The goal will be to use computation to quickly screen this to see which of these ends of the molecule or functional groups of the molecule has stronger reactivity or selectivity for the mineral of interest. And that's going to help us to tailor the design of new novel collector system or ligand system or collectors. So computation is definitely going to be playing a lot of role in that thing. You want to understand what kind of chemistry is going on there. A lot of these things, when you do them at the lab scale, you don't really know what chemistry is going on. And that's why I call computation molecular microscopy. We are basically a microscopic tool as well, but now we are looking at things from the atomistic picture. So I understand which atom wants to bind to another atom. I understand which one doesn't want to bind. How strongly do they want to bind? What electronic transfers are taking place? Those are things that are needed as we develop new collector systems, especially if we want to go towards the ones that are greener, the ones that are more environmentally friendly, taking some insight and knowledge from natural carboxylic acid. So that's where modeling is going to be playing a lot of role, so that we know the composition of the material, we know the surface chemistry of the material, and therefore know which collectors are going to be binding and those that are going to be rejected. And then we can inform our experimental collaborators and let them know that if you want to really selectively pick these minerals of interest, these are the kind of functional groups that you need, and this is the way you should be developing them. Yeah.
Thank you so much. Quickly, let me just run through for that other questions. Also from Ikechi Ofia Kalu. So yeah, I think this is just like a follow-up question.
Yeah.
To our first question. So for electronic structure property relationship, how does the density of state, DOS, relate to the energy performance of
the material?
Of the material.
Yeah, it's a very good question. It should be pretty straightforward to answer. So typically when you have a let's say for instance, you have a solar cell application and they are typically based on semiconductor. So therefore your ability to predict the band gap of the material, it's going to be very critical because your absorption properties have ability for it to absorb the solar radiation is based on the band gap the material has. And the band gap and the density of states are very correlated. The only thing you learn more from the dust is you get the same band gap, but you also be able to tell that if I sight an electron from a valence band, where is it going to go in the conduction band? So the dust can tell you that. The dust can tell you that you may be sighting from the valence band of oxygen P to maybe a zirconium D within that material. So you don't only say there's a citation, you even nail down where is that electron coming from, which orbital, and which orbital is going to collect it. So typically in solar cell, if you want your material to perform very well, you want a band gap between 1.1 to 1.5. Those are the optimal ranges for maximum solar radiation usage in the visible region. So we designing material, for instance, taking that paper we published in Advanced Material with the Markasite system, for somebody to tell us that the band gap is 0.3, it means that it's already completely out of the optimum range. So nobody will want to even use that material for solar cell. But then just using computation, we could go back to that problem and understand that the band gap of that material is even close to 1.2, which is still falling within the optimal region, and therefore should give us an appetite to say, how do we engineer this material to work in our favor? So those are the kind of things that dust or band structure gives you. And once you know, higher absorbance will reflect into higher performance. If you design material that can absorb the solar radiation, it means that you cannot even convert any of it to useful energy. So that is how they are correlated together.
Thank you so much for the response. So also, I think the last question for today, this is coming from the Dean School of Engineering, Dr. Vitalis Aye. He is saying, thank you so much for this intriguing and insightful talk. So this is his question. In the interface engineering modeling of system, such as the energy storage systems, how do we capture the presence of various types of defects that may occur in practice, ranging from interfacial cracks to precipitates that may form as a result of phase transitions that can happen in service?
Yeah, absolutely. So that is a very important question, and that's a very good topic that Vitalis is raising. So the good news is that one of the DOE grants I recently got is actually trying to address that problem. It's typically something we are not addressing. So typically most interfaces, when you form them, they may start off as very, very good, but you have to understand that under thermal stress and the photon stress and all these stresses that will happen, there can be all kinds of defects that may propagate for long time usage of this. So therefore, developing models that will be able to capture the evolution of the interface as a function of time, as a function of temperature, as a function of pressure is what is going to be very important. So one of the approaches we could do that, yes, they can be integrated. It's just they are generally very difficult to do, and that's why a lot of people don't do it. But I think it's long overdue that we begin to pay a lot of attention. Maybe that's one of the reasons why my grant was funded, because it's a very difficult problem, but we need to solve it. And therefore, we are going to be developing a new approach where we call simulated amorphization. Amorphization simply means that we're going to allow the system to evolve. So we will take that system. If I want to look at two interfaces, I'm going to take a support system, and I'm going to completely dissolve the material sitting on top of it, and then allow it to recrystallize. So the recrystallization is going to be driven by several factors. During the recrystallization process, that's when those defects, those cracks, all those grain boundary dislocations are going to happen. So typically, that's not currently done in a lot of models. And those are the things that we are beginning to pay a lot of attention to. So we're going to be you should be on the lookout for those models. We're going to be working extensively on this simulated amorphization, where we're going to be allowing the system to completely melt, recrystallize, form all these natural propagations of cracks and defects, and then now see how do they actually evolve as you change the temperature, as you change the pressure, and as a function of time. And I think those informations are needed, especially when we want to develop this robust system that will last longer, and therefore those understandings are going to be critical. So it definitely is a very good question Vitalis has raised here.
Thank you very much. We have really outshot our time. So the guest speaker I've actually shared with us his email. We can do well to reach out to him. I can speak for him. He is open to collaboration, and he's open to more. So if you can reach out to him directly, kindly reach out to him. If you need to also go through me, currently we are, we work, together at the Penn State. I could also as well connect you. This is one of the reasons why we organize this webinar. Essentially, is to create an avenue to collaborate, to provide a platform for collaboration for faculties in Africa with some of the Africans in diaspora on how we can together solve a critical problem that actually affects us as a people. And so I would like to thank you so much for joining the meeting today. Because of our time, as I earlier promised, I will not be able to ask for comments. It's already about 33 minutes above the time. So in the interest of the time, I would like us to just conclude on that note today. But reach out to me if you need to talk to Dr. Nelson for further collaboration, as he had actually mentioned. For the November edition, of this webinar, I'm also proud to tell you that we will also be inviting one of AUST alumni as well, who will be talking to us on how we can enjoy the opportunity that is provided by ASEIDA. Which is also the guest speaker is also, I think, he's also the assistant chair of ASEIDA. We will be having one of the ASEIDA leader speak to us for the November edition on how we can benefit from what ASEIDA is doing at the Penn State, how we can collaborate, as African scholars, and that will be the topic. That will be the focus for the November edition of this webinar series. I also thank so much. I also appreciate the president of the institution. I really appreciate Professor Eli Bala, the heads of department, Petroleum Engineering and Energy Resources at AUST. Thanks so much to all the staff of the School of Engineering, the Mechanical Engineering Department, and the entire AUST family. We also appreciate the PhD student joining us today for this conversation. Thanks to all our friends. We really appreciate the time you've taken to be part of us today. And of course, to folks here at Penn State as well who have actually joined, it's really, we really appreciate that the time you've taken to be part of us today. If you need this recording, I would like to get a permission from the guest speaker, you know, and then I'm going to send it to you. Also, if we get the permission of the guest speaker, this will also be available possibly on one of our YouTube channels so that you can listen to it again. Better still, you can also have access. You can also have access to the webinar for last month. That's September webinar. It's available on the YouTube. You can also get an access to that and listen to what was actually discussed in that webinar as well. Thank you so much. And of course, I will not take this for granted. Our guest webinar, you know, he has been a very good mentor, and he's doing much more to keep mentoring people who are ready to learn from him. And I must say, he is also going to welcome you to collaborate with you and to see that you succeed in everything that you do. From my side today, I think that's all that I need to do. Stay tuned. Watch out for the e-flyer for the November edition. And just like I'd mentioned, we will be having a gay on board, another AUST alumni who is doing great work here at the Penn State. And then I will see you at that time. So enjoy the best of the day. Here in the United States, just getting started with the day. Have the whole fun, you know, for today. And I would like to say bye from here.
Thank you, David.
Yeah, thank you so much. Bye.